Good morning, everyone. So I ended up having to re-record this lecture due to some technical problems, but it's okay because I had a chance to revise the notes for the better, I think. So we're talking about Chapter 6, which is on the topic of capacitance and inductance, and we have talked about those previously in the framework of how to deal with them for AC, steady-state AC problems, but we have not dived into exactly what they are physically. So the first section is on capacitors. A capacitor is a circuit element that consists of two conducting surfaces separated by a non-conducting or dielectric or insulating material. And so you can see here from this figure, the structure is pretty basic. We have two metal plates, which are going to be connected to the terminals of the device, and the metal plates are separated by this dielectric insulating material. We'll talk about this more later, but one of the interesting things about the capacitor is that DC current will not flow through the capacitor in steady state because there is no closed loop path for current to flow. And so the structure, which again we'll talk about more in a second, facilitates the buildup of an electric field between the two plates. There are many different types of capacitors, but for general applications, the types that we're going to talk about, the dielectric material may be composed of oil, wax, mylar, polystyrene, glass, ceramics. There's several interesting examples. Barium titanates facilitate very large capacitances. Glass and ceramic capacitors, which you see a lot, are most ideal for high frequencies. And there's a lot of other examples that you can refer to the book to read about. Now, stray capacitances may also be unintentionally present in a network, resulting from a voltage differential buildup between any two nodes or conducting materials that are insulated from one another. So the term stray capacitance refers to essentially unintentional capacitances present in a network. Capacitance is measured in coulombs per volt, or more commonly in farads. And the range of capacitors that we normally see is somewhere in the range of microfarads to picofarads. The values are normally small. The unit is named after Michael Faraday, the very famous physicist. Capacitors are energy storage devices, and the energy is stored as an electric field as that voltage differential build up between the plates. We'll see many parallels to the inductor, which also stores energy as a magnetic field. So what are the important relationships and equations to understand in order to work with capacitors? The first one is the definition of capacitance itself, which is defined as the dielectric or the permittivity of the dielectric insulating material times the area of the plates divided by the distance between the plates. And you can see those values are shown in this figure here. Capacitors are not always cylindrical in this manner. I just drew it for the purposes of demonstration. Now, charge is another important value. The charge that's stored within the capacitor is equal to the capacitance times the voltage across the terminals. So we see that capacitance represents the ratio between the charge stored and voltage. Next is current. Now, this is a very important relationship because it leads us to the next one. So the current through a capacitor is equal to the change in charge with respect to time. Current only flows through the capacitor when charge is being supplied to or drained from the capacitor's plates. Now, if we substitute in Q equals CV, then we get the next expression, which is I equals C dVt dt. And this here is one of the governing expressions that we are going to be using when we talk about capacitors. We can also flip that expression around and use integration in order to look at the definition of voltage with respect to current. And then the last two are power and energy. So power is always equal to voltage times current. And what we can do is, as you see in this purple line here, we can substitute in for I with dVt dt times C, and that gives us this version of the power equation here. Lastly is energy or work that's stored in the capacitor. This value is defined in joules, and it's equal to 1/2 C VT squared. So 1/2 C times the voltage across the capacitor squared. The next question that I'm going to pose here is what happens when a static, or DC, as well as a sinusoidal, or AC voltage are applied across the terminals of the capacitor. So first, let's look at the static condition. When we have a static or DC voltage being applied, the current will be equal to C times the derivative of a constant, which is ultimately going to be 0. So for DC circuits, no current flows through the capacitors and they act as open circuits. For sinusoidal or AC problems, what we see is that current does flow. IT will be equal to C times the derivative of the sine wave. I'm not going to go through all the details at the bottom here, but what we see is that current will flow in a sinusoidal form, just like the voltage. So now, we said that DC, and I should probably add something here, I should say steady state. What we saw was that, right, the capacitor acts as an open circuit for steady state DC problems. But what happens when we first connect a DC voltage source to a capacitor? Does anything different happen? And so what we see is an initial charging transient. So what I've drawn here are a couple different waveforms. They all relate to this circuit here, which is simply just a voltage source connected to a capacitor. This voltage source starts off, and then at the point T on, it turns on. And so you can see the red line represents the DC voltage being applied. During the charging interval, which is from here to here, the voltage builds up until it reaches its steady state value. And during that time, okay, so voltage is shown by the purple line. And during that time, current does flow, right? Because the dVc dt is not a constant. So during the charging interval, the orange line, which shows current, reaches a value which will be equal to C times the derivative of the slope for Vc during that time. And then once we get to T settle, which is when the transient settles, the current will drop back down to 0. So it's in this area going forward that we have the steady state, and that is when the cap acts like an open circuit. So just something to keep in mind, that when we talk about the capacitor acting like an open circuit for DC problems, that is for steady state. And later on in this class, we are going to talk about transients in a little bit more depth. So as with many things in this class, we are going to jump into an example, and it's going to help us to illustrate some of the ideas. In Chapter 6, there's not too many different types of problems that I can ask. Not anything compared to the Thevenin and Norton equivalent circuits or the chapter related to nodal or mesh analysis. However, there are a few concrete problems that I can ask you. So let's say we want to solve for the current through a 5 microfarad capacitor. I didn't draw a circuit because essentially it doesn't really matter. We know that there is a voltage, which is the blue line, that is applied across the capacitor. Now the answer is the green line. I already have it drawn, but let's pretend for a second that it's not already there. You'll see over here that the y-axis is labeled in blue for the voltages and in green for the current. So what do we need to do? We split the x-axis into 3 different regions, right? We have essentially region 1 here. We have region 2 over here, and then region 3, which we really don't care about because the voltage is flat, so we know there's no current going to be flowing. So how do we determine what the current is that's flowing in region 1? So we're going to take our expression C dV dt, and there's a discrete form of that. I can replace the dV dt with delta V delta t. And then all I have to do is simply plug in my values. So we know what the capacitance is. The slope here will be 24/6. And when we plug those values in, we see that there's a constant current of 20 microamps, which is shown at this line. For region number 2, we do a similar calculation, except now our slope is going to be negative 24/2 because the drop happens in 2 seconds. So we take the same capacitance, multiply by negative 24/2, and we end up with a negative 60 microamp current value. There is a follow-up question to this. It asks us to calculate the energy stored in the capacitor at 6 microseconds, I guess. That should be just 6 seconds. And so the value there will be 1/2 the capacitance times whatever the voltage is, which is 24 volts. Anyway, we multiply all that out, and we end up with 1,440 microjoules. Okay, so I know we're moving relatively quickly. We did go over this in person in class, so I'm hoping this is more of a review and is not the first time you're seeing this. So the next section deals with inductors. So this is the other type of passive energy storage device that we're going to be talking about in this class. Again, we've already dealt with inductors in our Chapter 8 work, essentially analyzing AC circuits. So an inductor is a circuit element that's composed of a coiled conducting wire, and we all remember from physics what that does when current flows through any wire, and especially what happens when it flows through a coiled wire. And so this picture here shows what happens. So we have current flowing through this coiled wire. It's wrapped around some sort of a core. That could be a magnetic, ferromagnetic core, or it could just be air. And essentially the flowing current will generate a magnetic field. The magnetic flux lines are shown here in green. And right, the power is converted to the form of a magnetic field. So inductors are typically classified by the type of core used. Again, this is something I would refer you back to the book for. I'm not going to spend too much time talking about the different types of cores and what the advantages and disadvantages are. However, I would like for you to understand, this is important here, understanding the basic operation of how an inductor works. So like stray capacitance, which we talked about before, there can be stray inductances in a circuit. They can also be problematic, and that can be a result of any time where current flows and generates some sort of significant magnetic field. Inductance, which is normally denoted by the letter L, is defined in the Henry, named after American inventor Joseph Henry. Inductors, like I said before, are also an energy storage device, and they store energy as a magnetic field. So this section I made a little bit shorter here. What are the important relationships or equations to understand? The relationship between V and I is shown here. It's sort of the opposite of what we saw for the capacitor. As opposed to current being dependent on the derivative of voltage, we have voltage being equal to L times the derivative of current with respect to time. We can also flip that around using an integral. Power is defined as L times the current times the derivative of the current. And then again, energy stored in the inductor in joules is 1/2 L IT squared. So now, what happens when a static DC or sinusoidal, let's put an AC here, current flows through our inductor? I'm not going to go through all the math, but For static or for DC signals, the inductor acts like a short circuit. So that's the opposite of the capacitor, which acted like an open circuit. And for sinusoidal waveforms, for sinusoidal currents, we'll see a sinusoidal voltage across the terminals. Again, very similar to how we saw the capacitor react. Now, the next question I want to ask is one that takes us back to our work on AC analysis. So what happens when we examine the ratio of V to I, which is equal to Z, for both the capacitor and the inductor in the Laplace or the frequency domain? So in order to do that, what I've done is I take the VI relationship for the capacitor, I take the Laplace transform of both of them. That leaves me with IC of S as well as VC of S, and then this additional part over here. So the capacitance is a constant, so it can be pulled outside. Why do we have this S? Because when we take the Laplace transform of a derivative, we end up with S times that function. I'm going to go ahead and assume that the initial condition over here is 0. Okay, so if we rearrange this in order to get VC over IC, our result is 1 over SC. And we can substitute JW, or J omega, for our S, which gives us something that should look familiar, right? It gives us the expression for the impedance associated with a capacitor, 1 over J omega C. We can use the same process to determine the impedance for an inductor, which will be J omega L. Okay, so the last thing that we're going to do here, and unfortunately, because we are getting towards the end of the semester, we don't have time to go through as many examples with inductor and capacitor specific problems as I maybe want to. But this is one final example that we're going to take a look at. So let's calculate the total energy stored in this circuit here. It has a lot of different components. Voltage source, current source, both are DC. That's important to note. And then we have a whole array of resistors, inductors, and capacitors. So the first step, and this is probably I don't want to say the most important step, but it's the only one that's new to this chapter, is to redraw the circuit for DC steady state analysis. And so for that, what we're going to do is we are going to open circuit all of the caps, and we are going to short circuit all of the inductors. So 2 and 2. And what we end up with is a circuit that looks like this in the blue. Remember, we talked about this before, how to treat capacitors and inductors for DC steady state problems. Step number 2 is to apply, really it doesn't have to be nodal analysis, it can be any sort of analysis to solve the circuit above. I'm not going to go through those steps because hopefully by now we're all very familiar with how to solve these types of problems. And the result is VB, which is also VC1, the voltage across capacitor 1, is 16.2 volts. VC, which is also the voltage across capacitor 2, is 10.8 volts. And then we calculated directly the currents flowing through either of the inductors. IL1 and IL2 are negative 1.2 amps and 1.8 amps respectively. So the last step in this is to calculate the total energy stored by all of these devices. And with these 4 values, we have everything that we need in order to do that. So we calculate our energy stored within our capacitors using 1/2 CV squared. We calculate the energy stored within our inductors using 1/2 LI squared. And that gives us these values: 2.62 millijoules, 2.92 millijoules, 1.44 millijoules, and 6.48 millijoules. The sum of all those together is our 13.46 millijoules. And so that gives us the answer to this problem here, which is what is the total energy stored within the circuit. So perhaps this was a little bit faster than we would have done it in class if I were in front of everyone. But I think this gives us a pretty good overview of issues specific to inductors and capacitors only. It introduces us to the components and provides a good, it supports all the information that we learned in Chapter 8 when we dealt with these types of devices in AC circuits.